Hey Geometry, this is actually the last lesson in Unit 3 about 3D figures. This one is how do 3D printers work? So here we see a right circular cone. We know it's a right circular cone because the vertex meets the base at a right angle. The base of the cone is in plane S. Planes P, Q, and R are parallel to S. Plane P contains the vertex, so there's the top, there's the bottom, and two planes in between. You have this in your classwork. I'm moving on to the next slide so we can talk about it. I'll point out really quick that like plane R slices it at a disc. So I've got a disc here because it's a solid figure. Here I've got another disc and a point, and then the base is a disc. Here we have it says sketch a cross section of point P of the cone by plane P. Okay, point P, right up there. Then with the next layer down, sketch the cross section of Q prime, which is the disc on plane Q, the disc on plane R, and the disc on plane S. So to sketch each one of these cross sections, we would need to know the radius of each disc. This is just a point, but for all of these, we would have to know the radius of each disc. And then it's just a circle with the radius that's given. The sketches that were in my teacher's manual, which are much better than the circles that I can draw by hand. So B, what happens to the cross sections as we look at them, starting with P prime and work towards S prime? Well, they get bigger, right? Because we're moving down the layers of the cone, the discs get bigger. So the intersection of plane P with the cone is a point, and each successive cross section is a disc of greater radius, therefore greater area, than the previous disc. So if I gave you guys some styrofoam and I asked you to make a disc, I just gave you a big sheet of styrofoam, and I asked you to make a cone, you would just cut successive discs, larger and larger and larger, and then stack, hopefully it's thin styrofoam, then stack them up on top of each other until you get to the top. Hopefully your accuracy is a little bit better than mine. Your radius, that your radius doesn't increase by too much for each layer so that you don't have all of these extra pieces here. But I guess you could also cut away those extra pieces once you stack them on top of each other. I mean, you guys would get really creative. That would be a lot of fun. We'll have to think about that as a tinkering project. We could also figure out the area of each disc because we know the radius, or we could figure out the volume of each disc because our styrofoam is going to have a little bit of height. And if we did the volume of each disc, because it has some height, we could add those up and get the volume of the cone. Remember we discussed that with Cavalieri's principle and how the volume of each piece sitting on top of each other equals the volume of the whole cone. What else could I tell you about this? I think that's it. So yeah, that'd be fun. All right, let's try this. Sketch 5 evenly spaced horizontal cross sections made with the following figure. I went ahead and copied mine in. So we would take this figure and slice it. I can't give you the perspective of slicing it with how this disc, goodness, what would we call this? This figure is laid out on my paper, but with each slice, it would get progressively thicker and then back down to thinner. So we've got thicker and then back down to thinner for each slice, right? And each one of these is parallel to the other. Now, this example gives us a coffee cup. Let's try drawing cross sections of the coffee cup. So the textbook's already given us, the cross sections. So we've got layer 5, layer 4, which is going to be a hollow disc plus the handle. Layer 3, I've got, that'll be interesting to figure out. Layer 2, which will be much thinner, and then layer 1, which is the thinnest and the biggest radius. So yeah, we've got layer 5, layer 4, which will be probably thinner than that with your handle. Layer 3 should be thinner with like the top of the handle, etc. Let's look. Well, that's the blanks that you have. I should have done the last drawings on this page. Let me get you a better drawing though. There we go. That one looks pretty good. Slightly like mine. So if you guys have been down to the tinkering studio and watched the 3D printer in use, like I could sit and watch it for a while because it's sort of fun how it just layers and layers and layers and layers. I've attached a few videos to your Google Classroom to show you how 3D printers work with a coffee cup actually, and then just a general piece of, I don't know, figure, I guess. So I would recommend just watching those really quick because we may talk about them in assessment. But during our problem set, we're actually going to use our 3D printer idea and the filament that's used to make figures and the density and the volume to figure out how much of that filament is used to make a certain object. So that's where we're going next. All right, a cone with a radius of 5 centimeters and a height of 8 centimeters is to be printed from a 3D printer. The medium, which is the material that the printer will use, which is what they call the ink of a 3D printer, is a type of plastic that comes in coils of tubing and has a radius of 1 1/3 centimeters. What length of tubing is needed to complete the printing of this cone? So we need to know how much, I guess we can do the volume of the cone and then try to figure out how much of that medium is needed. So let's figure out the volume first. I've got a radius of 5 centimeters and a height of 8 centimeters. So our equation for volume of a cone, pi r squared times h. Do a little math. I've got 200 pi over 3. Okay, now as far as the medium, like what shape is this? This tubing is a long, long cone. We don't know the height of the cone though, right? So the volume of the cone is pi r squared times h. We don't know our h. So let's simplify this. I've got pi, let's do that 4/3 squared times h, which is 16 over 9 pi. pi over 9 times h. So we've got two volumes, and I bet we know that this volume is going to equal this volume. We just need to solve for h. So we're going to set these equal to each other. 200 pi over 3 equals 16 pi over 9 times h. I think my pi is going to cancel out. Multiply by 9, divide by 16, and I've got h equals 37.5 centimeters. That's how much tubing I need to make that cone. Very cool. All right, let's do number 4. Don't let that distract you. A cylindrical dessert, 8 centimeters in diameter, is to be created using a type of 3D printer specially designed for gourmet kitchens. That's so cool. The printer will pipe, or in other words, print out the delicious filling of the dessert as a solid cylinder. Each dessert requires 300 centimeters cubed of filling. There's my volume. Approximately how many layers does each dessert have if each layer is 3 millimeters thick? So we have a cylinder. Each layer is 3 millimeters thick. Each dessert requires 300 centimeters cubed of filling. The cylindrical dessert's diameter is 8 centimeters, so we're going to go straight to 4 centimeters for the radius. So where do we go from here? Well, we know the volume, we know the radius, we don't know the height, right? So we have 300, oh that's funny, that was a pretty 300 centimeters cubed equals pi r squared times h. So I'm going to divide both sides by pi and 16. I'm left with h equals 300 divided by pi divided by 16 gives me 5.968 centimeters. So the total height of the dessert is, let's just go for about 6 centimeters. We can go ahead and round that up. It's dessert, so it's not scientific. Each layer is 3 millimeters thick. 3 millimeters is the same as 0.3 centimeters. So 3 millimeters, I move the decimal over one place, is 0.3 centimeters. The height, oops, I erased too much. The height is really the thickness of the layer times the number of layers. So we know the height is 6 centimeters. We'll stick with the more accurate one for a second. Equals 0.3 centimeters times the number of layers. If we divide both sides by 0.3, we get the number of layers at approximately 19.89. Well, we're going to say about 20 layers per dessert. That was sort of fun. I wonder what that dessert tastes like. Like, what are they putting in that piping? Is it chocolate, whipped cream? All right, let's try the last one. The image shown to the right is of a fine tube that is printed from a 3D printer that prints replacement parts. If each layer is 2 millimeters thick, so this way, each layer is 2 millimeters thick. I can't read that. Oh my goodness, I can't write today. 2 millimeters thick, and the printer prints at a rate of roughly 1 layer. Oh my. Every 3 seconds. How many minutes will it take to print the tube? So if we can do 1 layer in 3 seconds, and each layer is 2 millimeters thick, we can figure out how fast we're printing. So we're just going to go like this, 1/3 layers per second, because it's way easier to talk like that. So 1 layer over 3 seconds is the same as 1/3 layers per second. We've got our total height of the tube is 3.5 meters. We have to change 3.5 meters into centimeters. Millimeters would be good, but we're going to meet in the middle. So let's just do 3.5 meters. 1 meter is 100 centimeters. So I have 350 centimeters. That's the height of the tube. Now we know that each layer is 2 millimeters thick, and I'm not in the same units yet, so I need to change that into, I need to change my 2 millimeters into the same units as my height. I could have changed them in anything. I could have left this in meters, changed that to meters, change this to millimeters, which would be a very large number. I just need to pick a unit for all of them. So let's go ahead and change the 2 millimeters into centimeters. So I know 1,000 millimeters is 1 meter, and 1 meter is 100 centimeters. So I've got 2 zeros and 2 zeros. I need to divide by 10, so that's 0.2 centimeters, which at least now I'm good. .350 centimeters is my total height. Divide by 2.2 centimeters, which is each layer, gives me lots of layers. Those are the number of layers. And if I'm printing 1/3 of a layer per second, let's get a new color. I've got this many layers at 1/3 of a layer per second. I need to know how much time, because distance equals rate times time. So let's divide both sides by 1/3. And that gives me, handy dandy calculator, I'm actually timesing it by 3 then. 5,250 seconds. But what's the problem asking? How many minutes? So if I divide that by 60, 87.5 minutes. That has to be one of the most poorly laid out problems I've done in a long time. If you follow it from beginning to end, you can follow the whole thing, but if you just take a screenshot of this page, quite confusing. See if I can help a little bit. We start out here. Then we figured out the height in centimeters. Then we figured out what a layer is in centimeters. Then we figured out how many layers we would need to get the total height. And then we figured out how much time that would take. And then we divided that by 60 to turn our time into minutes. Phew. And that's the last slide. Awesome. Go ahead and watch the videos. I'm going to attach them to Classroom right now. And I thought this was a lot of fun because I love watching that 3D printer that we have in tinkering. Good job today.